Hi, my name is Sulaiman Ramadan, and my contribution for this project is custom data structure, which is my vector, my stack, and my queue. So we are not allowed to use the STL containers, such as std vector and std stack, and etc. So we used a dynamic array and templated. So all templated using dynamic memory and pointers. So starting with my vector is our dynamic array. It starts at capacity 8, and when it's full resize, doubles the capacity, copies everything into a bigger array, and frees the old one. So pushback, it stays amortized. As you can see, the pushback here. So when it's full size, the capacity, when it's reached the full capacity, it will enter this loop to call this function to get more capacity. So we use it for source lines, the tokens, and the list that owns every instruction pointer for cleanup. So for my stack is fixed 8 bytes LIFO. The spec fix the stack at 8 bytes, as you can see here. So push does the data top plus plus, and pop does the data minus top top minus minus top. Is empty and is full. These for letting the CPU crash safely on underflow or overflow. This backs the push and pop instructions. And now for my queue is a circular first in, first out. As you can see here, we have in the private this function grow, and we have this function in the public, which is enqueue, and we have a dequeue. Move tail and head with percentage cap, so they wrap around and reuse slots, no shifting. Grow double capacity and rebacks when full. The runner enqueues every instruction and dequeues them in order because a program runs first in, first out. Now we will try the factorial.sim file. We can see here in factorial, push R0 puts 24 into my stack, and pop R2 takes it back. LIFO round trip, it prints 24, and the dump shows R2 equal 24. My vector and my queue are doing the work behind the scene the whole time. And that's it for my part.
So, hi everyone, my name is Muhammad Adil Arif bin Azari, student ID 24-2UC244L6. So, in this project, in this assignment, my contribution was implementing the register hierarchy, general register, flag register, as well as the memory classes of our virtual machines. So these classes are all responsible for storing and also managing the processor data during program execution. So we can see, as you can see on my screen right now, this is one of the parts that I did, in which is the register hierarchy class. So first of all, the register class is the base class for all the process registers in this entire VM machine. So it stores a signed byte value and also provides provide functions to get and also set the register value. Also, it serves as the foundation of other register types, such as the general register, the derived register, and it also demonstrates inheritance by allowing the derived class to reuse its functionality and not overlap. So that's the function of the register class, as you can see here, the value, the return value, and all. So next, I also did the general register. Here you can see here the general register class. So the general register class inherits from the register class and represents the 8 general purpose register, which is R0 to R7. So each register stores values used by the assembly instructions during the entire execution of the program. So by inheriting from the base class, we avoid duplicating common register operations. As you can see, the usage of inheritance in our class here. So next, I also did the flag register. As you can see here, I implemented the 4 processes status flags, which is overflow flag, OF, underflow flag, UF, carry flag, CF, and also ZF, zero flag. So these flags are automatically updated after arithmetic operations of the instructions are completed, and it will indicate the result of the most recent calculations in the output of the program. So that is for flag registers. So I also did another part, which not in another class, which is the memory class. So the memory class here in our program stimulates the virtual machine's main memory by providing 64 bytes of storage. It supports reading and also writing values, while ensuring that memory addresses remain within the valid range. So instructions such as load and store interact directly with this memory class. So might as well do some demonstrations to indicate what actually I did for this. So as you can see here, I will start running the one of the samples. We will do the samples pack. Yes. So let's see how it runs. Here, as you can see, the program executes successfully. So the R1 here, R0, R1 contains 11, R2, R3 contains the 44, and the memory location, as you can see here, it stores the 44, the value 44. And the program counter is updated, as you can see, 5. After executing the 5 instructions in the arithmetic. If you want to know what the instructions are, you can see in the report. And okay, and then you can see here the flags here. There's no indicator, which means that no arithmetic overflow, no underflow, no carry, or no zero result occurs. So the all processor flags remain cleared, as there are no flags. Okay. So in conclusion, my contribution focused on implementing the processor storage components of the virtual machines in which the register hierarchy, the flag register, and also the memory classes, which provide data storage required by the CPU, and also instruction classes to execute assembly programs correctly. So thank you so much. That's all from me.
Hello everyone, my name is Azzam and I was responsible for the CPU and the instruction classes. The CPU is the main part of our virtual machine. It works with the register, memory, flags, and the stack to execute every instruction. It also provides function to read and write registers, access, memory, update the program counter, and manage the stack. This is the MOV instruction. It copies data from one place to other. It can move a value directly into a register, copy data between registers, or load data from memory into a register. This helps prepare data before other instructions are executed. This class performs arithmetic operations. It supports ADD, SUB, MUL, DIV, INC, and DEC. It reads the value, performs the calculation, updates the CPU flags, and stores the result back into the register. The flags tell us if the register is zero, overflow, or underflow. This class handles input and output. Display prints the value of a register. Input reads a value from the user. It checks that the value is between minus 128 and 127, then stores it and updates the CPU flags. This class handles shift and rotate instructions. It supports SHL, SHR, ROL, and ROR. Shift moves the bytes left or right. Rotate moves the byte in a circle without losing them. Then the new value is stored back into a register. These instructions work with memory. Load reads data from memory into a register. Store writes data from a register into a memory. This allows the CPU to move data between registers and memory. This class handles stack operations. Push saves a value onto the stack. Pop takes the last value from the stack and puts it back into a register. These instructions are useful for saving temporary data. This instruction resets the CPU flags. It clears flags like carry, overflow, underflow, or zero when needed. To conclude it, my part was implementing the CPU and its instructions. I implemented instructions for moving data, arithmetic operations, input and output, memory access, stack operations, shift operations, and resetting flags. Together, these instructions allow the virtual machine to execute assembly programs correctly. Thank you so much.
Good evening. My name is Khalid Baizid. Today I will be discussing my virtual machines assignment for OOPDS. And so today I'll be going over the things I did. So let's start. Okay, so as part of my assignment, I actually helped create the parser helper. Now in the parser helper, I actually helped make the tokenized function, which actually helps to split sentences into individual command words. These are the expected tokens that I have added. Now the code that I put in isolates operations and memory addresses using spaces and commas. And then I built the runner class. Now this actually helps load, decode, and execute the program. And I actually created a readline function. Oh yeah, the readlines function, which opens the document and extracts the text. And then I created and then this function also removes inline comments and blank spaces. But at the same time, I also worked on the main function, which runs the whole program, overall program as a whole. And my and then there's also the decode functions, which I worked on, which helps to evaluate isolated words, and the logic translate text strings into instruction objects as displayed here. And also the expected token function, or expected tokens, that you can see here, actually helps to checks the different parameters to prevent crashes. And the load function actually places every generated object into an execution queue, and which maintains the chronological order of operations. And my run method actually controls the main execution loop, and the program extracts one instruction from the queue and sends the object into the processor. The processor executes my requested operation, and the loop just repeats it until the queue is emptied. The main block actually initializes the system parameters, and the dump to all function, triggers it actually triggers after the execution of the loop, and it commands the processor to export the film final hardware state, and the program writes the data to a text document. So that is my entire part and my contributions to this assignment. Thank you very much.